are ready to go for another day? Very good. So I have again good news and bad news today. The good news is we're only going to solve one problem. The bad news is that it's going to take 2 hours. Although maybe that's good news as well, because in the problem that we're going to solve today, there are many interesting ideas that you can also use to solve other problems, either in data-driven control or even in more general systems and control problems. So maybe I changed my mind and I only have good news this morning. So the particular problem that I'm going to focus on is data-driven stabilization using noisy input state data. Before I start though, I want to quickly go over the outline of today's lecture. So I will start by explaining this problem of stabilization using noisy data. I will then present a sufficient condition. To come up with necessary and sufficient conditions, though, I need some tools. So I will first study the classical S-lemma, developed by Jakubowicz. Then I will talk about an extension to the matrix case, so we'll talk about the matrix S-lemma. And using that, then finally, we will be able to come up with necessary and sufficient conditions for data-driven stabilization. In this first part of the lecture, I will focus on a specific type of noise model, but then finally, in item 6 here, we will also generalize this to a general noise model. And then finally, I will also make another generalization to rank deficient data. Okay, so that's roughly the outline of today's lecture. To make a connection to the previous lecture of Kanat yesterday, I want to quickly go over the framework that we're considering. So, what is the framework? Well, we consider some known model class of systems. Could be LTI systems, parametrized nonlinear systems, in state space form or transfer matrix models, but we have some given model class. Within this model class, there is some unknown system S over here. It's unknown in the sense that we do not have a model for the system S. Luckily though, we can collect some data, D, that is generated by this unknown system S. And on the basis of this data, we can make a distinction. There are systems in this model class, M, that are falsified by the data. So those are the systems over here. And those systems cannot generate this data D. So they're falsified. They cannot be the true system S. So we can discard them, we don't have to work with them. On the other hand, there are also these systems in this green region over here, and those are all systems that are consistent with the data. In other words, all those systems could have generated the data set D. In particular, because our data comes from this true system S, also S is within this set sigma D, right? Also, sigma D consists of all systems consistent with the data. All of these systems in sigma D could have generated the data. Now let's also look at the system property P that we could be interested in. Yesterday we already saw some examples like controllability, stability. And we can also consider control objectives like stabilization, for instance. Then we said that the data are informative for this property P if all systems in sigma D have this same property P. What is the reasoning behind this? Suppose that I want to check whether my true system S is controllable, for instance. I can only do that if I know that all systems in this green region sigma D are controllable. Because if there's a single one here that is uncontrollable, in principle that could be the true system. We don't know. We cannot distinguish the true system from any other system in this region sigma D. So if that system is uncontrollable, then I don't know whether my true system is controllable. But if I can verify whether all systems in sigma D are controllable, then of course we know that also the true system is controllable. That's the reasoning. Similarly, we call the data informative for control objective O if there exists a single controller, C, that achieves this objective for all the systems in sigma D. So there the goal is to find a single controller that works for all these systems consistent with the data. And I view data-driven control design as using the data D to find such a controller C that works for all these data consistent systems. So that's the framework. Now, yesterday Kanat already talked about a number of problems, both analysis and design problems, all using noise-free data. Now, today I want to continue by also talking about noise. The case that we have then is, in the case of noisy data, we always end up with a set of systems consistent with the data. So it's almost never the case that this set sigma D becomes a singleton. That is something very different from the noise-free case. Because in the noise-free case, if you remember the lecture on Monday, if you would apply a persistently exciting input, then in principle I would be able to uniquely identify the system. So this set sigma D would collapse to a single system. That's never the case in the noisy case. In a noisy case, you always have a set sigma D of data consistent systems. Okay. Let's talk about the setup then. I'll consider, again, input state systems. U is the input, X is the state. And W here is what we call a process noise term. It's a noise term affecting the dynamics of our system. And this noise term is not measured. So we do not have access to Wt at time t. By the way, maybe at this point I can explain a little bit about this particular way the noise affects your system. This is a type of process noise or disturbance, you could also say. Maybe you've seen that already in another context. That's one way of having noise affecting your dynamics. There are also other types of noise, like measurement noise. What is measurement noise? Well, you could think of, instead of measuring exactly x of t, I measure x of t plus some noise term Wt. That's another description of your noise. That's called measurement noise. The tools that we develop today can also be used to solve such problems with measurement noise. But for today, I will just focus on this situation where we have process noise. And actually, both the situations of process noise and measurement noise, they're both relevant. But to keep the lecture a bit focused, I will just focus on the process noise case. Okay? Good. Yeah, so we have this system now. As before, I do not assume that we have a model of the system, which means that these matrices AS and BS are unknown. They're not given. But luckily, we obtain this data, obtained from this true system, and we collect samples, X, of the state, so x0, x1 to xt, so we have t plus 1 samples of the state. And in addition to that, we also collect the matrix U minus, which consists of t samples of the input. So U0, U1, up to U t minus 1. Notice that I stress here, W is not part of the data. So we do not measure W. Only the U and the X are part of the data. Okay. Well, what is the goal of today? I want to use the data, U minus X, to find the feedback law, U is Kx, such that this closed loop system, xt plus 1 is as plus bsk, xt, is asymptotically stable. That's equivalent to saying that the matrix as plus bsk is a stable matrix. That means, since we are dealing with a discrete time system, all of the eigenvalues of the matrix AS plus BSK are within the unit disk. So they have all modulus strictly less than 1. Right? That's what it means for a matrix to be stable. So this is my goal. I want to come up with such a controller K. Now, one thing I want to note is that this is impossible to do without making any assumptions about the noise, WT. Is that something that you already see? Could you explain that? Why would this be impossible if I do not make any assumptions about WT? So if WT can be anything. What do you think? Yeah, so if you don't have any idea about the noise, right? Well, indeed, so it's related to that. The model class is everything because the point is that if I take any arbitrary A matrix now in Rn by n and any B matrix in Rn by m, since the noise can be anything, yeah, in principle I could also have a noise, Wt, which is equal to xt plus 1 minus axt minus but. Which means that these dynamics are satisfied for this AB, meaning that any pair AB is in principle consistent with the state and input measurements. So then, yeah, the set sigma D would then be the whole model class, M. And of course, I cannot find a controller which stabilizes this whole model class of systems AB. Right? So without making an assumption about the noise, we're completely doomed. We cannot do anything. So, that's why I continue now and I start with making an assumption on the noise. Let's have a look at this assumption. So I'm going to assume that the matrix W minus, which collects W0, W1 up to WT minus 1. By the way, that's also an unknown matrix, right? Because I do not measure the noise. It's unknown, but I assume it to satisfy a certain bound. Namely, the spectral norm of W minus is less than or equal to epsilon. And that's going to be our assumption. And the epsilon here is a given real number. So to a certain extent, you can interpret this as we assume that the noise is small. Right? The norm of the noise matrix is less than or equal to epsilon. No? Do you, by the way, all know what the spectral norm is, how that is defined? Or shall we go over the definition on the board? Are you very quiet, huh? You would like to see it? Yeah, sure, let's do it. So, let's say that we have a matrix M. So M is a real matrix n by m. The spectral norm of M is defined as the supremum over all vectors x in Rm such that the norm of x is 1. And I take here the supremum over the norm of mx. That's how we define the spectral norm. Sometimes we would also call this the induced 2 norm.
Epsilon, you like to include the 0 as well? Epsilon should be greater or equal to 0?
Epsilon should be greater or equal to 0, yeah.
So equality means there is no noise?
Exactly, yeah. Yeah, and then we're in the same situation as yesterday, right? We just have all of these samples are 0, indeed, and then we have the noiseless case. Yeah, true. Any questions about the noise model that we assume?
So the model class is now the one with W, right?
True, true. We now indeed, so, well, the set of explaining systems is going to change because there we impose this assumption about the W minus. Yeah. Yeah, indeed, you could, yeah, okay, that's actually a good question. So whether also the model class now, because indeed we do restrict the W in this case. So you could also say that indeed the model class is all these systems where the W now satisfies this bound, indeed. Yeah, yeah, that's a good point, yeah. And also, as we'll see, that also affects the set of explaining systems then. Yeah. Because there now also the bound on the noise comes into play. Yeah. Okay, I will use throughout the presentation positive definite and positive semi-definite matrices a lot. That's why I quickly want to recap just the definitions here. So recall, I don't want to insult your intelligence or anything, but I just want to make everything self-contained. So a matrix P is symmetric. Matrix P is called positive semi-definite if X transpose Px is greater or equal to 0 for all vectors X in Rn. And it's called positive definite if X transpose Px is greater than 0 for all non-zero vectors X. Now, these are the notions of positive semi-definite and positive definite matrices. I'll also use the shorthand notation, so P greater or equal to 0 means that P is positive semi-definite, and P greater than 0 means that P is positive definite. Moreover, sometimes I will use the notation P larger or equal to Q, which means that P minus Q is positive semi-definite. And similarly, you can define these notions for negative semi-definite matrices and negative definite matrices. So a matrix will be negative semi-definite if X transpose Px is less than or equal to 0 for all vectors X. Right? So, well, what's the point? Well, there's this nice if and only if condition for the norm of a matrix Z to be less than or equal to epsilon. In fact, the norm of Z is less than or equal to epsilon if and only if Z times Z transpose is less than or equal to epsilon squared times the identity, which means epsilon squared times the identity minus Z transpose is positive semi-definite. And we'll work with this condition later on. Yeah, so if I plug in that fact in our noise model, then you see that basically our assumption on the noise becomes like this. So W minus times W minus transpose is less than or equal to epsilon squared times the identity matrix. Okay. Good. Well, let's continue. So I introduce these shifts of the state sequence. So x minus goes from x0 up to xt minus 1, and x plus goes from x1 to xt. I do that because then I can formulate this set of data consistent systems. So sigma consists of all pairs A, B that are consistent with the data, which means in this setting that x plus must be ax minus plus bu minus plus w minus, right, because we have this additional noise term, where w minus satisfies our bound. This is the whole set of systems consistent with the data. Well, you could reformulate that a little bit. So in particular, we have two things here, right? So w minus in norm is less than or equal to epsilon. And we also know, due to this equation, that w minus is equal to x plus minus ax minus minus bu minus. That implies actually that this set sigma, in this case, consists of all pairs AB for which this matrix over here as norm less than or equal to epsilon. So x plus minus a x minus minus b u minus in norm is less than or equal to epsilon. Like this. Okay. Let's have a look at a simple example. So I take here the true system to have A as matrix 1, B as is also 1. Epsilon, the bound on the noise, I take 1 over 2. The data that I collect in this case, 1, 2, 0 for the state, 1, minus 2 for the input. Yeah, and in this case, indeed, the set sigma consists of all AB such that this bound is satisfied. We worked it out on the board. If you plug in now the expressions for x plus, x minus, and u minus, you can reformulate this. Because, again, remember that this matrix has norm less than or equal to epsilon if and only if this matrix times its transpose is less than or equal to epsilon squared times its identity. On the previous slide. I use that fact and I reformulate this inequality as such. Maybe you can check for yourself that that is indeed the case. But you see that we obtain this inequality in terms of A and B and epsilon squared. Yeah. Well, we can also plot now the set of systems which satisfy this bound. And it's this ellipse over here. So this green region consists of all AB pairs in the set sigma over here. And my goal, again, in the rest of the lecture is going to be to find a controller which stabilizes all systems in this green region. So all systems consistent with the data. Any questions about this, about the set of consistent systems? Is it clear? Yeah. Okay. Now, this is the most important definition in the whole presentation. So I want to formalize what it means to find a stabilizing controller for all these systems consistent with the data. So I introduce the following notion of informative data. I say that my data, u minus x, are informative for quadratic stabilization if there exists a feedback gain, k, and a matrix P, symmetric m by m matrix, such that P is positive definite, and this Lyapunov inequality holds for all pairs AB in sigma. So what does this mean? What is the interpretation of this definition? Well, this means actually, so if the data are informative for quadratic stabilization, that means that A plus BK is stable for all AB in sigma. And the function that you see over here, so x transpose px, is a common quadratic Lyapunov function for all systems consistent with the data. So informativity for quadratic stabilization means we find a single controller that stabilizes all these systems consistent with the data with the same Lyapunov function. So this Lyapunov function is common for all systems consistent with the data. Okay. Maybe I can also provide a little bit more explanation. So when was a function a Lyapunov function again? Right? So a function is a Lyapunov function if it is itself positive definite. So Vx is positive for all non-zero x, and V at 0 is 0. So V is a positive definite function. And moreover, along the trajectories of our closed loop system, this Lyapunov function must decay. Meaning that if I evaluate v at xt plus 1, this must be smaller than v of xt. Let's see if that's indeed the case. So, if I plug in v xt plus 1, well, that's xt plus 1 transpose p xt plus 1, right? But I know that xt plus 1 is a plus bk xt. So xt plus 1 are trajectories of the closed loop system. So I plug it in here. But now you see something nice, because due to our Lyapunov inequality, this term in the middle over here, a plus bk transpose p a plus bk, is less than p. So this is less than x transpose px. But that's just our Lyapunov function evaluated at x of t. So indeed, along the trajectories of your system, this Lyapunov function decreases. And by a theorem of Lyapunov then, indeed, the closed loop system is stable. Asymptotically stable.
Here, you say that AB belongs to sigma.
Yes.
That sigma is for the noise-free case or the...
No, this is the sigma that we're considering. So all systems consistent with the noisy data. Yeah?
Would that mean that the equilibrium point is asymptotically stable? With W?
Okay, this is a very good question. Yeah. I understand where this question comes from. Let's go back to the objective. So basically, if I interpret your question correctly, you say, okay, during the experiment, there's this W affecting our dynamics, right? But what about after the experiment? So here, my objective is just to make A plus BK stable. Of course, if in a closed loop system here, we would also have a term plus W, then you would not have that the X state would go to 0. Then you could still ask, yeah, okay, what to do then, right? One possibility is then to make the effect of the W term on the state or an output of your system small, by means of H infinity control, for instance. That is something we'll treat tomorrow. But today I study kind of the preliminary problem, where we want to have internal stability of the following system. So if I would include this noise term Wt, I would obtain here this system. If I attach the controller, right? So I have this additional term over here. My goal today is to make this system internally stable, which means that this matrix is a stable matrix. That's the goal. But it's a very good question. And in fact, that also connects nicely to tomorrow's lecture. Because what Kanat is going to do then is suppose that in this system, we also want to make the effect of W small on some performance output. Yeah, you can also do that. Okay. Any other questions about this definition? No? Okay. Also, my goal here today is to find this control gain, K, and this common Lyapunov function that works for all systems consistent with the data. And I want to provide conditions under which the data are informative, and also give you a recipe how to compute such a controller K, if it exists, of course. So if the data are informative. Okay. Well, one important lemma that we're going to use is this Schur complement lemma. That talks about matrices that are partitioned in the following way. So who of you, by the way, are familiar with the Schur complements? Have some of you seen that before already? No, it doesn't seem to be the case. Okay, that's good. Then I'll go over everything. So the Schur complement lemma studies partitioned matrices. So imagine that we have some matrix S. It's a symmetric matrix, and it's partitioned in the following way. So we have S11, S12, S21, and S22. S11 is a symmetric matrix of size Q by Q. S12 is S21 transpose, and S22 is also a symmetric matrix, let's say of size R by R. But the question in the Schur complement lemma is, under which conditions is this matrix S positive definite? How can we verify that? The nice result is the following. So let's look at this statement 1. S is positive definite if and only if S22 is positive definite and another matrix is positive definite. This matrix is what we call the Schur complement of the matrix S. In particular, it's the Schur complement with respect to the matrix S22. So let's look at what is this Schur complement. Well, I will always think about it in this way. So we look at this partition matrix and we go clockwise. So the Schur complement is S11 minus S12 times S22 inverse times S21. That's the Schur complement, right? And the statement is, well, this matrix S is positive definite if and only if S22 is positive definite and the Schur complement is positive definite. So essentially you break up the positive definiteness of this matrix S in terms of positive definiteness of two smaller matrices. That's the point. Yeah, well, once you know one Schur complement, you can also do another one. So instead of taking the Schur complement with respect to the S22 block, I could also do the one with respect to the S11 block. So I could go in this way. I compute S22 minus S21, S11 inverse, S12, so the matrix over here. And then a similar statement holds. So this whole matrix S is positive definite, right? This big partition matrix is positive definite if and only if the S11 block is positive definite and the Schur complement with respect to the S11 block is positive definite. So again, we break up the positive definiteness of a big matrix in terms of two smaller ones. Good. Yeah, now we're really on fire, of course, because now you ask yourself, what if I don't care about positive definiteness, but positive semi-definiteness? And you can also do that. So that's the third statement. So suppose that S22 is positive definite, then S is positive semi-definite. So just positive semi-definite, if and only if the Schur complement is positive semi-definite. And finally, you also have a statement with respect to the other Schur complement. Yeah? Okay, good. Well, an additional result that I will use is the fact that if you have a matrix P, which is symmetric, then it's positive definite if and only if the inverse is positive definite. That follows from the fact that the matrix is positive definite if and only if all the eigenvalues of the matrix are positive. And the eigenvalues of P inverse are just 1 over the eigenvalues of P. So if all the eigenvalues of P are positive, obviously 1 over those eigenvalues are also positive. So that's how this fact follows. So P is positive definite if and only if its inverse is positive definite. Great. Well, let's try to see this in action. So I'm going to work a little bit with the Lyapunov inequality that we had in the previous slide. So remember that before we defined this notion of informativity for quadratic stabilization. And we had this Lyapunov inequality over here. Now I claim that using the Schur complement lemma, P is positive definite and this Lyapunov inequality holds if and only if this big matrix over here is positive definite. Well, let's try and see if that works. So my proposal is we view this big matrix now as the matrix S over here. And then we're going to apply item 1. So let's write this big matrix. So I have something like P, A plus BK transpose, A plus BK, and P inverse, which is positive definite. Right, by item 1, that's equivalent to saying that the S22 block is positive definite. So P inverse is positive definite. And the Schur complement with respect to this 2-2 block is positive definite. So let's compute the Schur complement. As always, we go in this clockwise fashion. So this is P minus A plus BK transpose. P inverse inverse, so there you get the P, A plus BK. And this should be positive definite. Well, the positive definiteness of P inverse was equivalent to the positive definiteness of P. So this is equivalent to saying that P is positive definite, and indeed, the Lyapunov inequality holds. Great. So indeed, what I wrote on the slide was correct. Indeed, P is positive definite and the Lyapunov inequality holds if and only if this big matrix is positive definite. Right. Great. So my general rule of thumb is that every day I have to compute at least 5 Schur complements. So I propose that we do it once more. So I now apply item 2 of this Schur complement lemma. So I start again with this big matrix, the matrix S over here. And now I'm going to apply item 2. So what will happen then? Well, we start with the positive definiteness of this matrix over here, right? By item 2, this is equivalent, the positive definiteness of the big matrix is equivalent to saying that P is positive definite. That's the S11 matrix. And the Schur complement with respect to the S11 block is also positive definite. So this is P inverse minus A plus BK, P inverse, A plus BK transpose is positive definite. Well, we already know that P is positive definite if and only if P inverse is positive definite. So indeed, my conclusion is then that this whole big matrix is positive definite if and only if P inverse is positive definite and P inverse minus A plus BK, P inverse A plus BK transpose is also positive definite. Well, that tells you something interesting. Because in the Lyapunov inequality that we started with, I had this transpose here on the left, on A plus BK. But actually, by our calculations over here, turns out that I could also have put that transpose on the right. And these statements are completely equivalent. So there exists a P which is positive definite and satisfies this Lyapunov inequality if and only if there exists P inverse positive definite matrix satisfying this so-called dual Lyapunov inequality. So this is a dual Lyapunov inequality, again, because the transpose here appears on the right matrix, not on the left. let's summarize the progress that we made so far then. What we've proven then is that the data are informative for quadratic stabilization if and only if there exist matrices K and P, such that P is positive definite, and the dual Lyapunov inequality holds. Again, where I put the transpose here on the right. By the way, I swept a little bit under the rug the fact that I also redefined P as P inverse here, but I do understand that of course there exists a positive definite matrix P inverse if and only if there exists this positive definite matrix P. Now, so the conclusion is, instead of considering our original Lyapunov inequality with the transpose on the left, we could also study this dual Lyapunov inequality. That's the point. And that will become very important in our conditions for data informativity. Because I'm going to work in the rest of the presentation only with this dual Lyapunov inequality. Okay, let's try to understand this a little bit further. So I have this dual Lyapunov inequality, and I can rewrite that using the fact that A plus BK is A next to B times I over K as this inequality over here. So really, I don't do anything here. Huh? So this is a block diagonal matrix. Because of the zeros that you have over here, the products of these matrices are just identity times P times identity, which is the P matrix over here, minus AB times I over K, which is A plus BK, times P, which you see over here, times identity over K transpose times A transpose B transpose, which is simply A plus BK transpose. No, so this is just a reformulation of the dual Lyapunov inequality. But the reason I'm telling you this, and I'm showing you this inequality in this form, is that this is now a quadratic matrix inequality in the matrices A and B. So this inequality that we obtain finally, you can view as a quadratic inequality in these unknown matrices A and B. That's the point. Okay? Good. Well, that's not the full story. This is one way of obtaining a quadratic matrix inequality, but now I will obtain another one. Let's start again from the set sigma of data consistent systems. I remember it's given by all pairs AB, for which this norm is less than or equal to epsilon. As we saw before, that norm inequality is equivalent to this matrix times its transpose being less than or equal to epsilon squared identity. Moreover, since epsilon squared identity can be written as identity AB times this matrix over here, times I A transpose B transpose, right? Because the zeros cancel all the terms depending on A and B, and we just obtain this epsilon squared identity term because of the identities on left and right. This set of data consistent systems can also be written as a quadratic inequality in terms of A and B. Right? So the only thing that I do here is I plug in this expression for epsilon squared identity, which is given by this expression. I plug it in over here. I take everything to the right-hand side. Yeah, and then this is the inequality that you obtain. Nice. So we found yet another quadratic matrix inequality in A and B. Now, why is that important? That tells you something about the structure of this problem. Because what do we want to do, right? We want to find this common Lyapunov function and controller for all systems consistent with the data. But we can reformulate that question as following now. So when does there exist this Lyapunov matrix P and this controller K, such that all systems consistent with the data, equivalently, all systems satisfying this quadratic matrix inequality, also satisfy the Lyapunov inequality. In other words, the quadratic matrix inequality over here. So that's really the structure behind the problem. You want to understand under which conditions all solutions to one quadratic matrix inequality also satisfy a second quadratic matrix inequality. That's the point. Yeah, now the big question is, of course, when is this true? So when do there exist such P and K? That's what I want to investigate now. Are there any questions up to this point? So do you see the structure about two quadratic matrix inequalities? Okay. Good. Okay. I'll now start by giving a sufficient condition under which this is true. So a sufficient condition under which indeed such a P and K exist. And I reason in the following way. So let's assume that there exists a matrix K and a matrix P, and finally a real scalar alpha greater or equal to 0, such that P is positive definite and this matrix inequality holds. So what is this matrix inequality? Well, in the matrix in blue here, you recognize the matrix that was specifying the Lyapunov inequality. And here, the matrix in green, that is the matrix that is specifying the set of all systems consistent with the data. And I now assume that the blue matrix minus some scalar alpha times the green matrix is positive definite. That's my assumption. In fact, I assume that there exists K, P, and alpha such that this inequality holds. Okay, let's see what happens then if I do that. So let's say that we take some arbitrary system consistent with the data, AB. Since AB is in sigma if and only if this quadratic matrix inequality holds, we know that indeed this inequality is satisfied. What I do now is I multiply the inequality that we have here on the top from left by identity AB and from right by the transpose of that matrix. Now, so let's see what happens. So first of all, let me make some definitions. So the matrix in blue, let me call that M of P and K. And let's call the matrix in green, let's call that N. So what happens? Well, we started with this matrix inequality, right? What was the matrix inequality on the top? Well, it's simply M of P and K minus alpha times N is positive definite. Now multiply this whole thing from left by identity A transpose, B transpose. Well, the point is, if you multiply a matrix that is positive definite from right by full column rank matrix and from left by the transpose of that matrix, then you preserve positive definiteness. Which means that if I multiply this inequality now from right by this matrix, which obviously has full column rank, right, because we have this identity over here, from left by the transpose of that, the result is still positive definite. Okay, let's work this out. So the first term, I get identity A transpose B transpose times this matrix M of P and K. And then I still have the right-hand side, identity A transpose B transpose. And then now I take this second term to the right. Okay, so this becomes larger than alpha times identity A transpose B transpose times the matrix N over here times identity A transpose B transpose. Right? Aha, okay, good. But now I realize two things. The alpha that we took here was greater or equal to 0. So this guy is greater or equal to 0. Because AB is a system consistent with the data, this inequality holds. So this is greater or equal to 0. Yeah, but then the product here must be positive semi-definite. Great. So the conclusion then is this matrix M multiplied with identity A transpose B transpose and the transpose of that is a positive definite matrix because it's greater than some matrix which is positive semi-definite. Which means that for this system AB consistent with the data, indeed our Lyapunov inequality is satisfied. So the data are informative for quadratic stabilization. Yeah.
So we'll go a couple of slides back.
Of course. The definition of...
only the quadratic inequalities that we defined.
Okay, so one quadratic inequality is here, right?
So the next one.
Yes.
Yes. So what we did is essentially that we connected both of them using the scalar alpha.
Indeed. Yeah, so the story is like this. For the set of consistent systems, we have this norm bound, right? And I rewrite that as this quadratic inequality in terms of A and B. For the Lyapunov inequality, we also have this quadratic inequality for A and B. And now I'm assuming, indeed, that there exists this alpha and the P and K, such that M minus alpha N is positive definite.
So, but how do we know that alpha can be a scalar? We can also connect them using the generalized matrix.
In principle, yes. Yeah. So at the moment, this is just a sufficient condition. Meaning, if we assume this condition, then we know that the data are informative. What I want to study, and it's indeed a good question, like why do I need the scalar multiplier, right? Maybe I could look at the matrix multiplier or something. It turns out that scalar multipliers are always enough. We'll see that later in the lecture. So later on, I also want to study necessary and sufficient conditions. Yeah. Thanks. Other questions? No? So, yeah. Yes?
We are saying that positive semi-definite and makes positive definite. How is it like always greater than n?
So the matrix N itself is not positive semi-definite. But if I multiply n by identity A transpose B transpose and the transpose of that, then it's positive semi-definite. For any system A, B consistent with the data. But n itself is not necessarily positive semi-definite. In fact, it's never the case. So I think your question was like, how can this inequality hold, right? If n is positive semi-definite, right? But
Imply that multiply by that I A transpose B transpose, that expression left hand side always greater than the right hand side.
yeah, indeed. So we showed indeed that this is always greater than this, right? And that's positive semi-definite. Yeah. But we cannot say that for the matrices n and m individually. Does it make sense? Any other questions? Okay. Good. Yeah, so to summarize the result that we obtained then, I formulate this proposition. So what we've just proven on the previous slide and on the board is that the data are informative for quadratic stabilization if there exist matrices K, P, and a scalar alpha, such that P is positive definite, and this matrix inequality holds over here. Moreover, in that case, if you have a solution P, K, and alpha to this matrix inequality, then in fact this matrix K stabilizes all systems consistent with the data. Because the Lyapunov inequality holds for all systems consistent with the data. So let's have a look at another example of this. As in the previous example, I take epsilon to be 1 over 2, and I consider the same data, xu. Well, in this case, I can choose P to be 1, K to be -1, and alpha to be 1. And one can indeed verify that then the matrix inequality that we have obtained here, the triangle, indeed holds. So this matrix M minus alpha n is positive definite. If you want to check that yourself, just check the eigenvalues of this matrix. They're indeed all positive. So this is a positive definite matrix. Which means that indeed this inequality holds with K is -1, P is 1, and alpha is 1. Hence the data are informative for quadratic stabilization using this proposition. And the controller U is -x stabilizes all systems consistent with the data.
How do you solve this data for a general system?
Yeah, very good question. So this inequality is not so easy to solve. Just this inequality. What I'll do in the next slide, and the reason is that you have these products of P and K, so this is a nonlinear matrix inequality. What I'll do in the next slide is reformulate this inequality as a linear matrix inequality. And that we can solve. Yeah. No, that's using just a Schur complement argument. Yeah. But we'll see that. Okay. But indeed, that's a good question. So yeah, how to solve this matrix inequality is still a question, but I want to address that. Okay. Let me see. How are we doing in terms of time? Okay. I propose that we take a short break here and just have a tea or a coffee. And then we continue afterwards. Is that okay? Or? No? Okay, you want to wait a little bit longer? Yeah, that's also fine for me. It's being set up. Okay. That's fine. Then I'll continue with this question, like how to compute a solution to this matrix inequality, right? So, yeah, as we concluded before, we had this product in this matrix inequality, right? This P times K. So this is a nonlinear matrix inequality. but it turns out that we can reformulate that as a linear matrix inequality using a Schur complement argument and a change of variables. So let's go over the proposition. I claim that the data are informative for quadratic stabilization if there exist matrices L, P, and the scalar alpha, such that this matrix is positive definite. And moreover, if you find such a solution to this now linear matrix inequality, then the feedback gain K is LP inverse, stabilizes all systems in sigma. One nice aspect of this inequality is here you see that this matrix over here is linear in P and L, right? So there are no products of P with L involved here anymore. And also this is linear in alpha. And so this is a linear matrix inequality. And there exist tools, numerical tools to solve those linear matrix inequalities. We'll also see an example of that in the tutorial session this afternoon. Now, so this inequality is something that we can solve for P, L, and alpha. Now, let's see how to prove this result, also based on the previous slide. What we do is we take a Schur complement of this big 4x4 block matrix with respect to the 4-4 block, so with respect to this P over here. And I claim then that I get this matrix inequality over here. Let's see. So, I start from my inequality over here. So let me rewrite that a little bit. So the first three blocks are P 0, 0, 0, 0, minus P, minus L transpose, minus L, 0. And then I also have this additional term minus alpha times the matrix, what we call N, right? So N is just the first three block rows and three block columns of this matrix. So we have minus alpha N over here. Okay, that's not the full matrix, of course. We have also a fourth block. The 4-4 entry is P. Then we have 0, 0, L over here. And here we have the transpose of that. So 0, 0, L transpose, like this. And this whole thing should be positive definite. Okay, good. Well, let's go back to the Schur complement argument that we had. So what is my idea? Well, I want to use this now. The S is this whole matrix over here. And I treat this P over here as the S22 block. So I get that this is if and only if. So this is positive definite, if and only if P is positive definite. And, moreover, the Schur complement with respect to P is positive definite. So what is that? Well, I start again with the 1-1 block, so P 0, 0, 0, 0, minus P, minus L transpose, minus L, 0, minus alpha N, minus the 1-2 block, 0, 0, L, P inverse, times the 2-1 block, which is 0, 0, L transpose. And this should be positive definite. Okay. Yeah. But then when I absorb this L P inverse L transpose into the block here, this is indeed exactly the inequality that I obtain. Right? In other words, this is equivalent to saying that P is positive definite P 0, 0, 0, 0, minus P minus L transpose minus L, and then I have minus L P inverse L transpose minus alpha n is positive definite. Okay, final step. I now define K to be L P inverse. So let's try to plug it in here. So this becomes if and only if both P is positive definite, and by changing these variables now, I have P 0, 0, 0, 0 minus P. Well, minus L becomes minus Kp minus P K transpose, and then finally in the lower right corner I have minus K P K transpose. Minus alpha n is positive definite. And you see that this is precisely m minus alpha n is positive definite. Right? So then by the previous result on this slide, the data are informative. So the conclusion is, by doing this change of variables, right, K is L P inverse, and by using a Schur complement argument, as I have highlighted on the board, you can make this inequality a linear matrix inequality. Yeah? Okay. Well, but so far, the proposition that we have established is only an if condition. So we have now a sufficient condition for informativity for quadratic stabilization. At the moment, it's not clear whether this is also necessary or not. So the big question is, yeah, are the conditions that we just obtained, are they also necessary? Well, that answer to that question is not so easy. In fact, we need some tools to find that out. In fact, for that, I need a matrix version of the S lemma. But to start, I want to start just with the classical version of the S lemma. Yes? Yeah. Yeah, it's a very nice question. So your question is essentially, if I understand it correctly, suppose that they collect a large data set, so T is large. How expensive is it to solve this inequality, right? Well, one of the nice aspects about this inequality is, in fact, the size of the constraint here does not depend on the size of the data set. Because if we look, let's just do a counting argument. How many rows do we have here? Well, P is an n by m matrix, right? So we have n plus m plus n again. So this is an inequality which is 3n plus m by 3n plus m. So independent of the time horizon of the experiment, so independent of t. And the kind of reason is that, of course, this matrix X plus, that has a number of columns, t, which of course does depend on the time horizon. But that dimension t is collapsed in this product over here. So that's basically the idea. So this inequality, in principle, the size is independent of t. That could, yeah, so numerical error, okay. That could occur if this is very ill-conditioned. For instance, suppose that I have very large data and the entries of this matrix become extremely large. Then you may run into numerical problems. That's true, yeah. Yeah. But yeah, so for the examples that we're going to consider in the tutorial, in principle, there's no problem with that. Any other questions about this sufficient condition? No? Okay. So let me then continue. So, as I said, I'm on this quest of obtaining necessary and sufficient conditions. And an important ingredient in that is this classical S lemma. That was first proven by Jakubowicz in the paper over here. And the statement of the theorem is as follows. So it's a very interesting result already by itself. Huh? You can use it also for studying other problems. So let M and N be symmetric matrices, N by N. Then it turns out that X transpose MX is positive for all non-zero vectors X satisfying X transpose NX is greater or equal to 0. So in other words, one quadratic inequality implies another one, right? All solutions to one quadratic inequality also satisfy this other quadratic inequality. If and only if there exists a scalar alpha such that M minus alpha N is positive definite. So imagine someone enters this room with two quadratic inequalities, so with these two matrices M and N, and he wonders about the question, yeah, when are all solutions to one of these quadratic inequalities also solutions to this other quadratic inequality? Yeah, then you would say, I have no idea. How would I verify that? That's not clear. But what Jakubowicz managed to prove was that, in fact, that's equivalent just to a linear matrix inequality, right? Because I just need to find the scalar alpha such that M minus alpha N is positive definite. And then, in fact, I know that all solutions to this inequality in green are also solutions to the inequality in blue. Cool, huh? This is probably one of my favorites in whole of systems and control theory. Well, the if part of this result you can show quite easily. And the only if, similar to what Kanat was saying yesterday, the only if part is always the difficult part to show. Huh? But maybe at least I can show you the if part on the board. So, we assume that there exists an alpha such that this matrix inequality holds. Now let's X be an Rn and be non-zero. Such that if I compute X transpose N X, I get something non-negative. Then I need to prove that also the other inequality holds. What I do now is I multiply my matrix inequality from left by X transpose, from right by X, and I see the following. So X transpose M minus alpha N X. Well, that's of course something positive, right? Because M minus alpha N is a positive definite matrix. And this implies that if I just look at X transpose M X, well, this must be greater than alpha times X transpose NX. But the alpha was greater or equal to 0. And X transpose NX was also greater or equal to 0. So indeed, I conclude that X transpose mx is positive. So indeed, then the if statement here holds. Nice. Okay. Yeah, so this result was first proven by Jakubowicz. Originally, that was developed in the context of Luret systems. So these are linear systems in feedback with a static nonlinearity. Typically in that literature, what is assumed then is that this static nonlinearity satisfies certain bounds, called sector bounds. And you can study the stability of those systems. There, the S lemma was used. Also, a non-strict version of this lemma is available. So what do I mean by that? Well, you see here that the inequality on this blue matrix M, that's a strict inequality, right? But you can also study the non-strict version. But for our purposes, what we actually need is a matrix version of this S lemma. The reason is that in this S lemma over here, this X, that's just a vector in Rn. But remember before, we were multiplying these matrices M and N by matrices, identity over A transpose, B transpose. So then it's not enough to study vectors over here, but we need this matrix version. Okay. Is it time for a break now? What do you think? Yeah, let's go? Okay, let's have a break, and then after the break, we continue with this matrix version.